Graph Theory, Class 10, Video 3. In this video we're going to continue talking about colouring graphs. In particular, this time we're going to talk about cliques. So let's begin with the definition of a clique. So a subgraph of a graph is called a clique if the subgraph is isomorphic to a complete graph. It doesn't matter what type of complete graph, so K1, 2, 3, 4, 5, 6, whatever, as long as there is a subgraph which is isomorphic to a complete graph, that's called a clique. And the idea of a clique is supposed to be motivated by like real world interpretation of the word clique. Like a clique in the real world is a group of people who are really close and know each other really well, right? So if you think about a graph as modeling like vertices as people and edges as friendship, a clique is a subgraph where all of the people know each other really well. Okay, so a clique is a subgraph where everyone knows everyone in that subset of vertices. So that's what a clique is. The clique number of a graph is just the size of the largest clique. Okay, so any given graph will have many different cliques, sometimes different sizes, and the clique number is just the size of the largest clique. So let's do some examples. Okay, so all I want to do is find the clique number for both of these graphs. So for this first graph right here, remember a clique is a subgraph isomorphic to a complete graph. So maybe it's useful to remember what the complete graphs look like. K2 is very simple, it looks like this. K3 looks like this. K4 looks like this. Sorry. Which also looks like this. They're the same graph, and on and on and on. Okay, so can you spot one of these complete graphs living inside here? Well, yeah, I mean, it's very easy to spot a K2, right? K2 is very easy. There's tons of K2s everywhere. So that means that the clique number is at least 2. But you can also spot a K3, and it's not exactly hiding, it's sitting right there. That's a clique of size 3 right there. Okay, so that means that the clique number for this graph is 3. Well, okay, technically I should have argued that there is no clique of size 4, right? You can't find a clique of size 4 in this graph. You might think this looks promising, but it's actually missing this edge and this edge. So that's not a clique. Okay. If we move on to the second graph, same thing. I'm trying to find one of these complete graphs hidden inside this graph. I'm trying to find the biggest complete graph hidden inside this graph. And again, it's not exactly doing a good job at hiding. There's this graph right here, okay, which is equal to this graph, which is K4. And it's fairly clear to see that there's no K5. Okay, K5, if you remember, is like the pentagram. It's this graph here, and that's nowhere to be found inside here. So the clique number is equal to 4. Okay? And that's the end of this example. So now let's talk about why you care about clique numbers and how these relate to colouring. Because I want to get back to talking about colouring graphs. Okay? So to do that, I will use a theorem. It's a pretty straightforward theorem, and all it says is that for any graph, the clique number is less than or equal to the chromatic number. Okay? The clique number is less than or equal to the chromatic number. So there's this relationship between the size of the largest clique and the minimum number of colors needed to color a graph. Okay? And I'm not going to go into a detailed proof because I think it's one of these theorems where the proof is believable if you think about it for a moment. I mean, if we, for example, consider this graph right here, okay, then we know that the clique number is 4, which means that it secretly has a K4 hidden inside it, right there. And we also know from the previous video that the chromatic number of K4 is 4, right? So what I'm saying is you need 4 colors just to color this bit. And then you've got all the other bit to worry about on top of that. So that means that you're going to need at least as many colors as the size of the largest clique. You might need more colors. It's not always equal. It's an inequality. Sometimes it's equal and sometimes it's not. Okay, but if you have a clique of size 4, you're going to need at least 4 colors to color that clique, and thus at least 4 colors to color the whole graph. Okay, so that's the best proof that I'm going to tell you. Let's see why this theorem is useful. So it's useful for proving that you found the chromatic number. Okay, so if you recall this graph here, the question could be find the chromatic number and prove that it's the correct chromatic number. And prove that it is correct or minimal. As in, prove that the number you found is the smallest number of colors needed to color the graph. Well, it's pretty easy to do that for this graph, right? Like, I can color it like this, and I'll color this one and this one green. So the claim is that the chromatic number equals 3. But to actually prove this, I'm going to use this theorem here. Okay? And the way I'm going to do that is I'm going to say, well, look, there's a clique of size 3 right here. There's a clique of size 3 right there. So the clique number equals 3. Okay? But by this theorem, we know that the chromatic number is greater than or equal to the clique number. So by the theorem, we have that the chromatic number is greater than or equal to 3. Okay? But we already found a 3 coloring. Since we found a 3 coloring, we know that the chromatic number is less than or equal to 3, because this is our 3 coloring right here. Okay? Well, if you put these 2 pieces of information together, this piece of information and this piece of information, the chromatic number is greater than or equal to 3, and the chromatic number is less than or equal to 3. The only way that they're both true is if the chromatic number equals 3. Okay, and that's how you prove that the chromatic number is minimal. You use the clique inequality right here, and this helps you prove that the number that you found for the minimum number of colorings is actually minimal. Okay, this example I only did a very simple graph, but you can use this same technique on more complex graphs, like this graph here. Okay, exactly the same technique. So that's the end of this example, and that's the end of this video.